It is imperative that you know the difference between strong and weak acids. Strong acids dissociate or ionize 100%. Weak acids, on the other hand, dissociate or ionize less than 100%. In fact, most weak acids dissociate less than 50%. Because strong acids dissociate 100%, we can use stoichiometry to discover the concentration of the hydronium ion, which will be equal to the solution concentration. However, since weak acids dissociate out for the most part less than 50%, we cannot use stoichiometry and must revert back to our ICE table. Strong acids have a very high Ka value, while weak acids have a low Ka value. Strong acids have a high electrical conductivity since it is a strong electrolyte. Recall that 100% of the solution is in ion form. However, weak acids have a much lower electrical conductivity since less than 50% of the solution is in ion form. Recall the kinetics lab. Strong acids have a very fast reaction with metals and carbonate compounds, while weak acids have a slower rate of reaction. Strong acids have a low pH value on the pH scale. Most strong acids have a pH of 1 or less, or for the most part between 0 and 2, while weak acids have a higher pH value. Since strong acids have a low pH value, you will see a very intense or deep color on the indicator paper, while weak acids will have a lighter shade. Over the next few lessons, we're going to look at weak acids. In today's lesson, we're going to look at the pH of a weak acid and the percent reaction associated with that. The dissociation of a weak acid is less than 100%, as stated above. The percent reaction with water of a weak acid is the fraction of acid molecules that dissociate or ionize compared with the initial concentration of that acid. For an acid of a general formula HA, where HA represents the acid, if we react this with water, we are going to have the hydronium ion and just A negative, meaning that HA is the acid, so it donates the proton to water to give us H3O positive and A negative. If we're looking for the percent reaction, and again, percent reaction is the fraction of the acid molecules, which is represented by H3O positive, over the initial concentration of the general acid HA times 100%. This is a formula that you are responsible for remembering. Let's go through an example. The concentration of the hydronium ions was found to be 3.3 times 10 to the negative 4 moles per liter in a 0.25 molar carbonic acid solution. What is the percent reaction of this acid? Well, we just covered that percent reaction is equal to the hydronium ion concentration over the acid. In this case, it would be carbonic acid. You can just represent that as HA if you wish, or you can look up the formula for carbonic acid off your acids and bases strengths table. Therefore, percent reaction is the hydronium ion, and we are told that the hydronium ions were found to be 3.3 times 10 to the negative 4 molar. So we have 3.3 times 10 to the negative 4 molar over the acid, which we were told was 0.25 molar, times 100%. Notice here that we have molar over molar, so those units will cancel to leave us with just percent, and this would be 0.13%. Calculate the pH of a 0.1 molar oxalic acid solution. Seems like a straightforward question, one that we've seen before. However, notice that the question asked us to calculate the pH of an oxalic acid solution. If you find oxalic acid in the acids and bases strengths table, you'll notice that this is in fact a weak acid. So it's not as straightforward as it seems. However, we've been asked to calculate the pH of a 0.1 molar oxalic acid solution, and a 0.1 molar solution is the magic concentration. I call this the magic concentration because if you look at the top of your acids and bases strengths table, you will notice that the entire acids and bases strengths table is listed according to a concentration of 0.1 molar. So if you're ever asked a question about a 0.1 molar solution, you can go to the acids and bases strengths table. So again, I ask that you go to your acids and bases strengths table and find oxalic acid. Once you find oxalic acid on the acids and bases strengths table, I then want you to go to the percent dissociation column and determine the percent dissociation of oxalic acid. And when you do, you will notice that it has a percent reaction of 51%. Again, this only works for the magic concentration of 0.1 molar. So percent reaction is equal to the hydronium ion concentration over the acid concentration times 100%. We know that oxalic acid has a 51% reaction. We're looking for the hydronium ion concentration, and we know that we started with the acid concentration of the magic 0.1 molar. Rearranging this formula, you'll get an answer for the hydronium ion concentration to be 0.051 moles per liter. So again, we could not approach this question with stoichiometry because we do not have a strong acid. We have a weak acid, so we cannot use stoichiometry. However, we were given the magic concentration of 0.1 molar. Since we have the 0.1 molar concentration, we can use the acids and bases strengths table to find the percent reaction. If we're given a question about a weak acid and we don't have the magic concentration, then we're forced to use ice tables, which we'll cover in a little bit. To finally answer the question, we know that pH is equal to negative log of H3O positive. We just found the concentration of H3O positive to be 0.051. Recalling the rules of significant figures, we have two significant figures in our concentration, so we should have two decimal places in our pH, and this would be 1.29.